Hello everyone, welcome back to my channel Ace to Excel. In today's video, we'll be talking about synchronous counter. Synchronous counter are those counters which has common clock. Synchronous counters always have common clock. The term common clock means that every flip-flop will be triggered at same time by same clock. Whenever we get a question on synchronous counter, there are few fixed steps of solving a synchronous counter. So I'll first tell you the main steps. Main steps of solving a synchronous counter are: first step, you need to decide number of flip-flops required, which are indirectly gathered from number of bits a counter has. 2-bit means two flip-flop circuits, 3-bit means 3 flip-flop circuits. So you need to keep it in mind that number of flip-flops required will be indirectly fetched from number of bits a specific counter circuit have. So along with number of flip-flops, you must know the type of flip-flop you are going to use for the designing. Step 2, whatever type you have decided, depending upon that type, you need to make the excitation table of the flip-flop. If you are using type T, you will make excitation table of T flip-flop. If you are using JK, you will make excitation table of JK flip-flop. Step 3 is state diagram. Now I'll first define what is state diagram. State diagram is a closed loop diagram which tells you the various states the counter will count. If I say state diagram, let us say we are making mod 4 counter, that means 2-bit counter. The state diagram will be 0 0 0 1 1 0 1 1, from 0 0 to 0 1, from 0 1 to 1 0, from 1 0 to 1 1, and from 1 1 back to 1 0. Do keep in mind it is a closed loop and state diagram is incomplete if you do not put the arrows. Arrow here shows that I am making it for an up counter. After making the state diagram, in the same step, you will also make circuit excitation table. Circuit excitation table. What is circuit excitation table? Circuit excitation table will talk about present state, next state, and flip-flop, whichever is used. If it is JK, JK. If it is used T, then T. That are the main columns of a circuit excitation table. And step 4, with the help of K-map, you will design the circuit. Right. So now we will try to design one simple synchronous counter, and for our ease, I will be using mod 8. That means 3-bit synchronous up counter. Now, mod 8 means it will count 8 states from 0 0 0 to 1 1 1. Because the counter is up counter, increasing order of counting will be done. Whatever mod is, do keep in mind synchronous counters will always have one 4-step phenomena for its. Now the steps are, first one, number of flip-flops required. Now as the question says, it is 3 bits, so 3 flip-flops will be required. Second thing, type of flip-flop to be used. I am defining that I'll be using type of flip-flop as T. That means step 2, which is excitation table. So I'll be making excitation table of T flip-flop. Excitation table, as you know, consists of these values: present state, next state, and now if I consider 2 inputs Qn and Qn plus 1, 4 possible combinations are there: 0 0, 0 1, 1 0, 1 1. Now do keep in mind, T flip-flop means toggle flip-flop. Toggle flip-flop, the concept of toggle flip-flop is that if value is 0, it remains in the previous state. And if value is 1, it toggles. That is, if it is previously 0, it will change its state to 1. If it is previously 1, it will change its state to 0. Now if you look at the table, present state is 0, next state is 0, somewhere it is a scenario of hold. If it is a scenario of hold, that means T is equal to 0. Now check the second one. Present state is 0, next state is 1. There is change of state, that means T would be 1. Again, present state is 1, next state is 0. Again, value is toggling, so T will be 1. Now, present state is 1, next state is 1, somewhere hold is there, that means T is equal to 0. So this is how you get the excitation table of T flip-flop. Step 3 says state diagram. State diagram is totally dependent upon modulus of a counter, and we are designing mod 8. That means there are 8 states in a state diagram, which I am writing in the binary from 000 to 111. So somewhere it is 000, 0101, 010, 011, 100, 101, 110 and 111. These are the 8 states. And if it is up counter, somewhere it is from 000, it changes its value to 001, then 0101 to 010, then to next state, then to next state, and in this way a closed loop between these 8 states are established. This makes our state diagram. State diagram is always a closed loop diagram, and somewhere state diagram is from one state to another state. A connectivity is established, and that makes a state diagram. This is how a state diagram of synchronous 3-bit up counter looks like. Now, with the help of the state diagram, we can make circuit excitation table. Circuit excitation table always have 3 elements: present state, next state, and flip-flop required. Now because we are using 3-bit or mod 8 counter, there are 3 present states: QA, QB, QC. There are 3 next states: QA plus, QB plus, QC plus, and there are 3 flip-flops: TA, TB, TC. Do keep in mind, TA is MSB, TC is LSB. Now how we design? For designing, always start from the present state. Present state is 000, present state is 001, present state is 010, then it is 011, 100, 101, 110, 111. Now, if you will look on the state diagram, from present state 000, it goes to 001. So in front of 000, we write 001. From 001 it goes to 010. So from 001 we'll write the next state in front of it as 010. Then in this way we will quickly complete our next state table. Somewhere we will uplift them by level 1, and at the last state we know it is again returning back to all zeros. Now using the excitation table we will check how the states are changing, and we will check it for every flip-flop. Talk about QA. Present state is 0, next state is 0. That means it is hold, TA is 0. Talk about present state is 0, next state is 0, again value of TA is 0. Present state is 0, next state is 0, again TA will be 0. Next value, present state 0, next state 1, toggling happens, that means T is equal to 1. Present state 1, next state 1. State is still the same, no doubt it is 1 and 1, that means output is 0. Then present state 1, next state 1, 0. Present state 1, next state 1, 0. Present state 1, next state 0, toggling happens. This is how we complete the table for TA. Similarly, we'll quickly complete the table for TB and TC. And this is how TB appears. TC, which is the LSB bit, always changes. So we never map it for synchronous counter, and TC's value will always be 1. Now, with the help of this, we will make a K-map. 3 different K-maps will be made, one for TA, another for TB, another for TC. So I'll quickly make the K-map for TA. It is 3 bits. K-map will be 8 cell. The elements of K-map are QA, QB, QC, 00, 01, 11, 10, 0, 1, 2, 3, 4, 5, 6, 7. That is how we number the K-map. And for our ease, I am writing small values here so that it is easier for us to label the cells directly from this figure. Now if you see, it is high at 3 and it is high at 7. So I am putting at 3 and 7. Similarly, I will be plotting it for TB. Again, value is QA, QB, QC. If you get the values, I'll number the cells first. 0, 1, 2, 3, 4, 5, 6, 7. Now this time it is high at 1, 3, 5, 7. 1, 3, 5, 7. Third one, which is for TC, somewhere it is all high. Without naming even, we could write, but if I'll number the cells, this is how your values appear. This is for TA, this is for TB, this is for TC. Now TA, if you pair up, gives you the value as QB, QC. TB is a quad and the value for this. Now if you see the quad, I'm giving you a quick revision of K-maps as well. This is how your cell changes. QA varies while QB also varies. The only stable factor is QC. So TB will be equal to QC while TC is equal to 1. This is complete step. And now once we are done with the circuit excitation table and K-map, we'll be drawing the diagram. For diagram, it is crystal clear in the circuit itself. There are 3 flip-flops. So I'll quickly make 3 boxes. These 3 boxes will be named first. A is the MSB and C is the LSB bit. So I'm naming it as it is. Type of counter is synchronous. Synchronous counter is made up of same clock You can use positive, you can use negative clock, choice is yours. Now we are using the flip-flop as T. So I'm quickly labeling the values as TC, QC, QC bar, TB, QB, QB bar, TA, QA, QA bar. Now, the first value of TC shows TC should be attached to 1. So, I have attached TC to high. Second value is TB and TB shows it should be connected to QC. So, I am making the connections quickly. And I am changing the color so that you can understand that this is how the connection works. Now, next is TA. TA is getting two values. One is QB, another is QC. So, I am taking it as QB and QC. Multiplication is required. So, we need an AND gate. And this AND gate's output, which is QB, QC, is given to TA. And this is known as QA, MSB and QC, LSB, and this is how you will design mod 8 3-bit synchronous up counter. I hope you have understood the topic. If you have any doubts, you can reach me